Now we're going to talk about compression. Compression is a dynamics process, meaning that it's dealing with volumes, from the loudest volume to the quietest volume within a given source material. In order to demonstrate this and explain it, I'm going to open up one instance of the FabFilter Pro C2. The reason I'm using this is just like the Pro Q3 EQ plugin, it gives a very good visual representation of exactly what's going on. Now, before we start to go through each individual parameter and explain what they do, it's a good idea to understand why we would be using compression in the first place. The main reason for using compression is to gain consistency within the dynamic range of a specific sound. This basically means closing the gap between the loudest part of the sound and the quietest part of the sound. There may be things within your source material that are very loud in certain areas, where the majority is fairly low in volume. A compressor will give more consistency and less range of volume between the loudest part to the quietest part. Let's look through these individual parameters and explain exactly what they mean. Let's start with the threshold. The threshold is the volume that we set to determine where compression will start from. If I play this kick drum, you'll be able to see the volume of the kick drum represented against this vertical axis. You can see here that our kick drum is peaking just above -6 decibels. At the moment, our threshold is set to 0 dB FS. This basically means no compression is going to happen unless the volume of our source material goes above 0 decibels. At the moment, we're under that because we're peaking just above -6. In order to make compression happen or be detected, we need to bring our threshold down past the peak point of our kick. So let's do that and see that visually represented within the plugin. As you can see here, the green line shows the volume moving up, and the crosshair shows at which point we are going to start compressing. So we can see everything above this dotted line will now go into compression. But so far, nothing is happening. This is because our ratio is set at 1:1. Ratio determines how much our volume will be brought down once it has breached our threshold line. If you remember ratios from school, these are basic division calculations. So 1:1 means itself, or nothing. Nothing will happen. What goes in comes out. If I change this now to something like 2:1, you can see here our volume has gone down once it has breached the threshold. Now when I press play, you will see compression characteristic represented by this red line. This is known as gain reduction because the volume or gain has been reduced. The higher the ratio, the more the gain reduction. Let's move all the way up to 10:1. So what's the difference between 10:1 and 2:1? If we think about this in a mathematical form, we have to divide it by 10. But what are we dividing by 10? We are basically dividing the volume breached past the threshold by the ratio number. So at 1:1, what breaches, what goes past, goes out. So there's going to be no compression happening. At 2:1, we are basically dividing the volume breached by 2. So for instance, if I was to breach the threshold by 10 decibels past the threshold line, the volume would get brought down to 1 decibel. Because our ratio is 10:1. It is divided by 10. This, I understand, can get very confusing. However, if you try and think about it logically, all you're doing is dividing the amount of volume breached by whatever the ratio equation is. So 2:1 will be half of itself. 10:1 would be divided by 10. Higher than that, whatever the number is, as long as the ratio is a number to 1, all you are doing is dividing the number breached by the ratio number. The threshold decides at what point compression will start to happen, or where the compressor will start to detect volume, and the ratio decides how much that signal will be brought down in volume once we have breached the threshold line. Now, the ratio and the threshold on some compressors may have something called a knee control. If I move this, you will see the relationship between the threshold and ratio changes. Hard knee means that as soon as the threshold is breached, the ratio will come into play and gain reduction will happen. But it will not happen until it has been breached. If I make this more of a softer knee, you can see that the curve softens out, giving us a smoother journey into our desired ratio setting. A harder knee gives you more obvious compression. It's easier to hear and easier to pinpoint when something's been compressed, because it goes from not compressed at all to straight away being compressed by whatever our ratio number is. A softer knee gives a smoother compression characteristic, making it more transparent and less obvious to the ear. We're going to keep this just at hard knee for now, just to make sure that you can see a better or less confusing visual representation. If I lower the threshold, more of that kick drum signal will be detected by the compressor. As you can see now, all of this signal here is being compressed, whereas before, if I lift the threshold, all we're doing is getting rid of those initial peaks. Remember, anything below the threshold line does not get compressed. It is not detected by the compressor and it gets untouched. A threshold of very low means the majority of the volume will be compressed. A very low threshold in conjunction with a very high ratio means we can pretty much eradicate the sound. Let's move it back to 2:1. Just so we understand that all we are doing is halving the volume breached from that threshold, and lift the threshold a bit more, just so we can see exactly what it is that we are dealing with. So as you can see, all of this area here of the kick drums is being compressed, anything below is uncompressed. Next, we need to move on to the attack and the release. These two, just like the threshold and ratio, are related with each other. It's a common misconception that the attack time determines how fast the compressor starts to work. This is not the case. What the attack time does is it determines how fast it will take once the volume has breached a threshold to be pulled down to your desired ratio amount. A very fast attack means that it will be pulled down once breached very quickly. A slow attack means that once it's been breached, it will start to compress straight away, but it will take longer to fall down to our desired ratio amount. The release time determines how long it takes to go back to being uncompressed again. So, a very fast release and a very fast attack mean that as soon as it has breached the threshold, the signal will be brought down to its desired ratio amount. Then as soon as it's reached that, it will snap back to where it was before, hopefully in time to then reach the next transient peak. Let's see this in action. As you can see, it instantly pulls down the volume once it's breached the threshold, and then releases that back to uncompressed before the next transient comes in. If I was to make this release longer, so it's a slow release, as you can see, it never fully goes back to being uncompressed because it's taken too long to snap back to an uncompressed condition. Let's make this faster. And as you can see, it releases fully. The longer the release is, the more consistency we get in our sound. For things like percussive elements and drums, longer releases aren't really a good idea, unless you want it to be fully consistent and not very pokey, not very prominent, transient, and sharp sounding. A longer release will soften out the volumes and make volumes a lot more consistent over a longer period of time. This works just the same with the attack times. If I slower the attack time, you'll see what it does as a visual representation of how long it will take to pull down to the relative ratio amount. As you can see here, this is represented by the initial pull down line. You can see it takes longer to go down in volume, meaning it doesn't fully hit its desired ratio amount. A fast attack means it happens instantly, with a fast release meaning as soon as it's reached its desired amount, it snaps back to uncompressed. If I slow this attack down, it never fully gets down to its desired ratio amount before another transient comes in, meaning that it's not really compressed as much because it doesn't have time to pull it down as much as we've wanted it to. A fast attack and slow release gives you this characteristic. What this is basically doing is as soon as that transient breaches the threshold, it holds onto it, but then it makes sure that it doesn't have enough time to release back in order to make it sound snappy. If I was to make this a slow attack and slow release, as you can see, it's a much more smoother characteristic. It takes a long time to reach its desired amount. It never fully reaches there because the next transients come in before it's had time to pull down fully, but then it keeps on holding it down with a longer release. This can give us a nice, warm, thick sound. Let's bypass. You can hear that drop in volume because we have dipped it by -6 decibels. This is where something called gain or makeup gain comes in. What we are doing is we are making up the gain that we have lost through compression. As you can see here, we're taking away 6 decibels. So what we can do is add towards that back into the signal. Let's bypass. So as you can see, we've taken away 6 here from gain reduction due to our threshold and ratio amounts and our attack and release relationship, and we've added that gain back in. If I bypass this now, the characteristic is it's thicker and warmer. This is because it is a lot more consistent in its kick volume. I'm going to show this as a representation with a bounce. So let's do this drastically so we can understand exactly what's going on. I'm going to pull the threshold all the way down. So we're covering a wider range of our audio signal. I'm going to put the ratio up to 4:1, meaning everything breached from this threshold line. Once it's breached, however much it's breached by will be divided by 4 and then brought down to a specific volume. I'm going to have a fairly fast attack, meaning that it's going to pull it down really hard. And then I'm going to have a slow release, meaning it's going to hold on to it. As you can see here, we're taking away -18 decibels in gain reduction. So I'm going to add in a little bit more, maybe add in 14 decibels here. And what we're going to do is come back to our track here. I've set up a compression visual bus. We're going to take our kicks output and send this straight to the compression visual bus and record it in. I've muted this just so we don't get to hear it, just so you can see what is going on. So let's take these 2 tracks. I'll move this up and let's have a look at a visual representation of what the compressor has done. Now, as you can see here, the difference between these two is drastic. The kick drum is louder for longer, The tail isn't as drastic as it was before because we have a longer release. It's taken longer to release that. And we have an initial snap. This is because our compressor, to begin with, took a while to start compressing. So what it did was it held that initial transient. Let's zoom in a bit more so we can see that as a transient mark. It let the initial part in, then it pulled it down because it took a while to start compressing. And then it took a while to then release that compression before the next one came in. The difference between this kick drum and this kick drum, if I open the volume of this a bit, we can see the dynamic range is more consistent from here to here. We can then make up that gain by making it a bit louder here, and we can see the volume of our tail is louder than it is on this one. It's a common misconception that compressors turn things up. They don't. Compressors turn things down. They compress the signal. It is up to you to then turn it up with your makeup gain, completely dependent on how much gain reduction has occurred. Next, we can look at something called range. On some compressors, you may not see this control. All range is a range or a limit to how much compression can happen. At the moment, we have set it so we can get a full amount of 60 decibels worth of gain reduction if we want to. However, if I don't want that to happen, I can make sure that regardless of however hard our ratio and threshold is, we will never go above 5 decibels worth of gain reduction. You can see that represented with the line. What happens is, I can always go down to about 5 decibels worth, but as soon as that happens, it lets go of the compression again. A little bit more, maybe 10 decibels of maximum compression range, or the full range. Lastly, we have something called sidechain. A sidechain basically determines what areas are going to be within the compression range. We've already decided what volumes are going to be within the compression range with our threshold line. However, we can decide what frequencies are going to be within that area. For instance, if I open up the sidechain here, it gives us an EQ curve. I can turn this on and say that any frequencies below 144 will be cut out of the compression detector. Same with the high range and same with the mid range. This again is completely up to you. This is a very comprehensive sidechain control within the Pro C2. Other compressors may just give you cuts in the low range and in the high range. This plugin, however, gives you full control over what frequency and your decibel per octave. So I can decide that everything below 95 Hertz will not be in the compression circuit. Let's have a listen and see what this does. As you can see, I covered the full range of frequency here, so my kick drum is being compressed to whatever my threshold, ratio, attack and release settings are. But if I take away the fundamental of the kick, all I'm compressing is frequencies higher than the dominant. I can do the same with the high frequencies, so all I'm doing is compressing the low range. This means I can really slam the very low range. Again, let's change this to a higher decibel per octave. Meaning only this range of frequency is being compressed.